All right, our last topic for this unit, bond enthalpy. You need to be able to define bond enthalpy. What I have here in bold, I've seen asked on so many IB exams. It'll say define bond enthalpy, and it's that clear. You need to make sure you have the word average in there. You need to make sure you have the word gaseous in there. You need to make sure you have 1 mole. So the average bond enthalpy is the energy needed to break 1 mole of bonds in a gaseous molecule averaged over similar compounds. I alluded in the last class, when I say averaged over similar compounds, I mean they assume that CH bonds are the same no matter what molecule they're in. We make an assumption that the CH bond here is equivalent to the CH bond there. It's not true, but it's the best we can do in these situations. Okay, I'll show you what we do with this in a minute. Another thing that you need to realize is that, another big thing, like big as in huge thing, bond forming releases energy, bond breaking requires energy. So when I separate 2 molecules, I have to do work to do it. When they go back together, energy is released. So breaking bond uses energy, making bonds releases energy. Requiring energy, endothermic. Releasing energy, exothermic. Okay. Bond enthalpy values are given in the data booklet. They're also on that pink card I gave you of heat of formations. They're on the back side of it down below. They might not be identical, but they'll be good enough for our purposes. All right, so first question going to be asked here is, are each of the following endothermic or exothermic? Remember, endothermic is going to be if we're going to break a bond. Exothermic is going to be if we're going to make a bond. So if I'm looking at A, I have 2 separate fluorines. They're going to come back together and join and make 1 molecule. So we're making a bond, exo. For the second example, CO2 solid to CO2 gas. Are molecules joining or molecules separating? They are breaking apart, their separation. So that's going to be endothermic. Feel free to try to think through the next couple before looking at the video. If you want to pause it, try to work through them and then come back and look at the solutions. It'd be a great idea. For C, I have gaseous water molecules coming together as a liquid. So they're coming together. I'm making a bond, exo. In D, I have fluorine with no charge joining up with an electron to form fluorine -1. I have 2 things coming together. I'm making a bond. That's also going to be exothermic. I'm having fun with colors here. Sorry if they're not all legible. Okay. For E, I have a potassium ion and an oxygen ion, and they are joining together. So once again, I'm making a bond, and it's going to be exo. Triple bonds, double bonds versus single bonds. So for example, I can have carbon triple bonded. I can have carbon double bonded to another carbon, or I can have carbon single bonded to another carbon. Which bond do you think is hardest to break? If you said single bond, you win. So, I'm sorry, if you said triple bond, you win. So this is the strongest bond. And this is the weakest. Since that's the strongest bond, it's going to have the highest bond enthalpy. And you'll see this reflected in your heat table. So if I scroll down here to where the values from the data booklet are, we've got single bonds in this table up here. And then if I compare like carbon-carbon double bond to carbon-carbon triple bond to a carbon-carbon single bond, you can see that the carbon-carbon triple bond has the highest bond energy and is the strongest bond. Highest bond energy means the hardest bond to break. Okay. You may also be asked to either write an equation that represents the bond enthalpy for something, or you may be asked to identify which equation represents it. So let's take a look at water. First of all, the definition of bond enthalpy says it needs to be gaseous. And I'm going to break it apart. I'm going to separate the H's from the O's. So I'm going to end up with 2 solo hydrogens and 1 solo oxygen, also in the gaseous form. How many bonds did I break? 2. The definition of bond enthalpy is it needs to be for 1 mole. So even though I broke 2 bonds, to convert this into being for 1 mole, the energy associated with this reaction would be the energy required to break 1 mole of the bonds. Okay. Another example. Br2 simply breaking apart into 2 Brs. What's missing from this equation? I need to have the phases. I do not need to add a fraction because only 1 bond was broken in separating Br from Br. Okay, our third example, CH4. So I'm going to take CH4 and separate it into carbon and 4 hydrogens. What's missing? Gas, gas, gas. How many bonds did I break here? I broke 4. So if I wanted the energy for 1 of them, I would divide the energy for this reaction by 1/4, or 1/4 CH4 goes to 1/4 C plus H, gas, gas, gas. Let's take a look at a couple multiple choice questions that ask you to apply this. So here, which equation represents the average bond enthalpy of the SH bond in SiH4? So if I have SiH4, I'm going to break it apart into these things. And I need to divide through by 1/4 because I broke 4 bonds. So this equation only breaks 1 bond, which means it's not going to count as average. The second equation looks pretty good. The third equation, no, because we're forming a new bond and we don't want that to happen. The fourth equation looks decent. We're starting in gases, we're ending in gases, but the problem is this would be the energy for 4 moles of bonds breaking, and we want the energy for 1 mole of bonds breaking, making B the correct answer. Okay, average, or the bond enthalpy of the HI bond. So in this case, we're just breaking 1 bond. Taking a look at my choices. A, I'm gonna reject because it has new bonds forming. B, I can reject for the same reason. C, I don't want to have charges present. D, correct. The reason I don't want to have charges present is it would also be the transfer of electrons, and that's not something that's taken into account with bond enthalpy. What's a second reason I could reject B? Besides the fact that we have new bonds forming, the second reason I could reject B is right there. Solid, not gaseous. Okay, we're gonna pause for a second.